Learning Outcome 8.4. Describe and draw the block diagram for amplitude modulation and asynchronous demodulation. This is together with Learning Outcome 8.5, calculate the modulation index, and Learning Outcome 8.6, determine the spectrum for all signals in an amplitude modulation process. As you saw in previous videos, the modulation process takes a signal, multiplies it in time by a cosine, and this produces an amplitude modulated signal with a given spectrum. Demodulation says what do we do with that to return our original signal and our original spectrum. For synchronous demodulation, we considered it from the frequency domain perspective. Here, we're going to consider it from the time domain perspective, looking at the time domain signals and what can we do with them to get our original x of t back. So we'll start with our modulated signal. We're aiming to get this signal here, our x of t back. Well, that x of t is all along here at the top, so if we want to get that, we need to get rid of the stuff on the bottom because we only want this. We can accomplish this with a full wave rectifier. Mathematically, this is just an absolute value. When we do that, we have all that extra signal component in the top, filling in the gaps which previously were empty. We're still aiming just to trace this envelope. So we want to get rid of all this high frequency changes. We can get rid of high frequencies by applying a low pass filter. It could be an ideal filter. The nice thing about asynchronous demodulation is you can quite often get away with a non-ideal filter and even one that's not extremely high order. There will be some level of jaggedness left. I've over-accentuated it here, but there will be some. It won't be perfect. But again, thinking about it like an engineer, if it works, that's okay. That's what we're aiming for, and we're pretty close to getting that through something which was extremely simple to implement. How would you implement a full wave rectifier in a circuit? Just a diode. What's the simplest low-pass filter you can implement in a circuit? Think a first-order low-pass filter. You can do it with two components, an RC circuit, one resistor, one capacitor. So the minimum that you need to implement this is one diode, one resistor, one capacitor. There's a few other things you would add to make it nice, but really that's all that you need. And years ago, when teenagers used to tinker around the house, people would build these in their living room. And you still could do that. If you're interested, let me know. Maybe we can set something up. This gives us our x of t, and this works very simply. Now I've been doing this with this as an example time signal. But this signal may not be representative of all signals we might get. What if that signal were to have a negative component to it? Modulate it still by the same cosine. We get our negative x of t, and we bounce back and forth. Still have an envelope function, but it's going to be a different envelope function this time. Spectrum is going to look the same. A different signal will have a different shaped spectrum, but it will still have a spectrum within a given band. And that spectrum will still shift to positive omega of 1 and negative omega 1. And its amplitude will be halved. Given that that's our new modulated time signal, how do we demodulate it with asynchronous demodulation? If we go through that full wave rectifier, okay, so far so good. Low pass filter, we get something out, but that's what we're trying to get. We wanted to get this, and that is not our x of t. Okay, why isn't it? It's these negative portions that messed us up. Well, don't give up. I told you people did this at home, so there must be a way around it. What we do is we look at our signal and we said, well, the problem was things were negative. Well, we can fix that by adding a constant to our entire signal. And that can shift our signal up to the point where everything is positive if we choose a value of a that is larger than the smallest negative value in our signal x of t. Well, let's look at the spectrum. Fourier transform of a constant is 2 pi times that constant times delta of j omega, an impulse at 0 with an area 2 pi a. Look in table 4.2. And then linearity because it's a and not 1. When we add this impulse to this triangle, the impulse sits there. The area of the impulse is 2 pi a. The amplitude of our triangle is 1. Because this is an area and this is an amplitude, they do not add. They both get registered as being there. And the amplitude at frequency 0 will actually be infinity, infinity plus 1. But we still list it as 1 because we're right there next to it. Modulate it. Now what does our spectrum look like? Cosine has those two impulses, one at positive omega of 1, one at negative omega 1. So we're going to shift this positive and negative, scale it by half. Now comes the term modulation index. This indicates how much did we shift our signal by. We take the maximum of the absolute value of x of t and divide it by a, the amount we're going to increment it by. Pretty straightforward to calculate. Write this down in your note sheet. Now let's review this whole process. Take our original signal, which has an original spectrum, increment it by some amount a, and that a can be anything that makes the whole thing positive. You can make it significantly higher or just a little bit higher. That gives us an x of t that's now strictly positive. Our spectrum will now include an impulse. We modulate. We get a spectrum and our time modulated signal. To demodulate, we pass our signal through a full wave rectifier and then through a low pass filter. Modulation is this portion here, although sometimes we think about it as including the addition. Our asynchronous demodulation is our full wave rectifier and our low pass filter. Now, one other point. What are the pros and cons of using asynchronous demodulation versus synchronous demodulation? This is a lot simpler. Why is this good? Well, if you're working for a company, you want to get paid. Therefore, you want that company to make money so it has money with which to pay you. If they can sell something for a low price, they can sell many of them. And if they sell many of them, they might make a profit, and therefore they might be able to pay you. The negative is we're now also transmitting this impulse. This impulse contains a lot of power. That means your radio station needs to have much more power available in order to transmit this signal. Well, if you've got a nice hydro dam nearby, nuclear reactor, coal-powered plant, whatever you're using for power, you're good to go. But if you're up on a satellite in outer space or deep in this ocean, transmitting this extra power may not be desirable. And therefore, for some applications, we care about the cost in the transmission more than the cost in the reception. And therefore, for an application such as space, they care to reduce the power in the transmission, and they'll pay more because they only need to have 1 or 2 radios that are able to receive the signal coming in from space. And they're willing to pay a little bit more money in order to build them, because they need to take your signal, determine what its phase is, which can be done with a phase lock loop, which historically was very expensive to implement, but now we've got chips where it's relatively cheap. And so for a space application, your space agency is willing to pay more for this than you would do if you're trying to market this to all the people around the country. Think about it.